Chapter 10. Thermodynamics. 10-to-1 relationship between heat and work. In a closed system there's a direct relationship between heat and work. Heat and work both transfer energy to or from a system. Key idea: a system never has heat or work, it has internal energy which is affected by heat in/out or work done on/by the system. Energy can be transferred to or from a substance as heat, changing its internal energy, plus/. The internal energy can be used to do work. Transfer of heat and work. System, a set of particles or interacting particles considered to be a distinct physical entity. Environment, the combination of conditions and influences outside a system that affects the behavior of the system. X of closed systems, a gas confined in a cylinder by a piston, a calorimeter, a thermos. Work done on or by a gas W equals P delta V is represented in the equation. W, in joules, J. P equals pressure in Pascal, Pa. 1 Pascal equals 1 N/m2. Delta V equals volume change in, M3. Sample problem. Gas in a container is at a pressure of 1.6 by 105 Pa and a volume of 4.0 cubic meters. What is the work by the gas if it expands at a constant pressure to twice its initial volume? Solution. P equals 1.6 by 105 Pa equals 1.6 by 105 N/m2 V equals Vf. Vi equals 8.0 cubic meters to 4.0 cubic meters equals 4.0 cubic meters. Width equals PVW equals 1.6 by 105 N/m2 4.0 cubic meters, W equals 6.4 by 105 J. Thermodynamic processes. Isovolumetric process. A thermodynamic process that takes place at a constant volume so that no work is done on or by the system. X, a car with closed windows parked in a hot garage. Isothermal process, a thermodynamic process that takes place at a constant temperature. X, usually a slow process like a balloon expanding slowly during the day. Adiabatic process, a thermodynamic process during which heat energy is transferred to or from the system. X, usually a fast process like filling a tank. Isobaric process, a process that takes place at a constant pressure. X, heating an open pot of water. 10.2 The first law of thermodynamics. The first law is a statement of conservation of energy that takes into account a system's internal energy, U, as well as the energy transfer to/ from the system by work and heat. It is expressed as signs of Q and W for a system. Delta Q equals positive if heat is added to a system. Delta Q equals negative if heat is released from a system. Delta W equals positive if work is done by the system. Delta W equals negative if work is done on the system. First law, isovolumetric process. Delta U equals Q, W delta V equals 0 since W equals P delta V, W equals 0 therefore, delta U equals Q. Energy added to the system increases the system's internal energy. Energy removed by heat decreases the system's internal energy. First law, isothermal process. Delta U equals Q, W since delta T equals 0, delta U equals 0 therefore Q equals W. Energy added to the system as heat is removed from the system is work done by the system. First law, adiabatic process. Delta U equals Q, W Q equals 0, therefore delta U equals -W. Work done on the system increases the system's internal energy. Work done by the system decreases the system's internal energy. First law, isobaric process. delta U equals Q, W since W equals P delta V, delta U equals Q, P delta V. Example, a gas inside a cylinder with a fitted piston. First law, isolated system. Delta U equals Q, W since Q equals W equals 0, delta U equals 0. No heat or work interaction with surroundings, so there's no change in the system's internal energy. Sample problem. A total of 135 J of work is done on a gaseous refrigerant as it undergoes compression. If the internal energy of the gas increases by 114 J during the process, what is the total amount of energy transferred as heat? Work done on the system is W. Solution W equals minus 135 J. Work done on the system is U equals 114 J. U equals Q, W. Q equals U plus W. Q equals 114 J plus, minus 135 J equals minus 21 J. Q equals minus 21 J. In this problem, energy is removed from the gas as heat, which is indicated by the negative sign on the Q value, Q less than 0. Cyclic processes. A thermodynamic process in which a system returns to the same conditions under which it started, no change in system's energy. Delta U net equals 0 and C net equals W net. Resembles an isothermal process in that all energy is transferred as work and heat. Example, operation of a refrigerator. The heat engine. Any device that exploits a temperature difference to do mechanical work. The net work done is equal to the difference in energy taken in as heat from a high temp reservoir, QH, and the energy expelled as heat to the low temp reservoir, QC. W net equals C net equals QH minus QC. Basically, a heat engine takes in heat from a hot place, uses some of it to do useful work and dumps the rest. The larger the temp difference, the more work done in a cycle. 10.3 The second law of thermodynamics states that no cyclic process that converts heat entirely into work is possible. Includes the requirement that a heat engine give up some energy at a lower temperature in order to do work. So a heat engine cannot transfer all energy as heat to do work. Second law of thermodynamics. No cyclic process that converts heat entirely into work is possible. Efficiency of a heat engine. The smaller the fraction of usable energy that an engine can provide, the lower its efficiency is. Efficiency equals can never be 1, or 100%. Sample problem. Find the efficiency of a gasoline engine that, during one cycle, receives 204 J of energy from combustion and loses 153 J as heat into the exhaust. Solution. QH equals 204 J, QC equals 153 J, F equals 1 QC, QH, F equals 1 153 J, 204 J, F equals 0.250 J. Entropy, a measure of the randomness or disorder of a system. A greater disorder means there is less energy to do work. The motion of the particles of a system is not well ordered and therefore is less useful for doing work.